The
achievement
is they give the numbers at the beginning of the
during the first 2 years of the study. How much do they themselves expect to achieve in the chosen field of study? It's an answer to a questionnaire, the same as well. How well do they integrate into the student group? And these soft science things become really important predictors. Here's a totally different study that started with 360 children at birth, and they were observed until 8 years with almost no dropout. Only 13 children dropped out because the parents moved and other things. And the special features of this study are really exceptional because it started with a random subsample of the general population where the study was taken. And then a sampling plan was done in which you have obstetric and how do we call the other? Psychosocial risk. So they were observed at some scores, but then the table was constructed low, low, high, high, and you had 40 in each cell. So heavy oversampling of children with high risk. That's a problem with many other studies, whether they are retrospective or prospective. As soon as you study rare events like risk for malformations or other things here, then you need huge sample sizes, or you can't say anything about the exposed groups. So here are the variables that we eventually defined. We look, what is the influence of these early risks on those that we can observe at 4.5 years and at 8 years. And the context variables we have taken, it is difficult to measure such things like psychosocial risk, biological motoric risk, obstetric risk in young children. But we found that taking the average score was helpful in the analysis. It's the first time they really can show strong dependencies. And here is what happens. We have a well-fitting graph for child development data, where indeed 2 measurements taken at 3 months. Does the family provide an unprotective environment? They are just not ready to have a child. They have financial, drug, alcohol problems, and so on. Or was a child hospitalized in the first 3 months? And these directly influence strongly cognitive deficits at the age of 8 years. And what you see here the first time is the graph alone is not enough. There are linear and non-linear relations, main effects and quadratic interactions. And therefore we have to supplement the graph by some additional information. And here you see, for instance, the average measurement of cognitive deficits depends as a main effect on unprotective environment, but if the unprotective environment is really poor, then this average score also increases over proportionally. That's what the YRE squared, for instance, means here. So Wilkinson's notation, Wilkinson is a well-known numerical analyst, and this notation was introduced in the context of generalized linear models a long time ago. Questions to that one?
The kids have separately the motoric deficit or cognitive deficit.
Yeah,
they have simultaneously. They have the same deficits together.
Well, they were selected in that particular way. There were 40 kids who had low, 40 kids who had high, some who had only one. So it's a whole group almost equally distributed. which is not representative of the population. And then in the actual analysis and interpretation, it becomes extremely important that we also have a subsample of what is the norm group, the random sample of the population. So far for two real examples. Now here is a medium-size regression graph in which I want to introduce you to the notion of concurrent variables. So you see what I call stacked boxes, G3 and G4. G3 is the top, I always number from the top down. And G5 and G6, they are stacked because there are no relation between the two groups within at that level. Okay? So what are the concurrent variables? Only those where there is at least one connecting line. So deleting all the errors from the previous graph leaves us with this picture. And then we see the stacked boxes even clearer. And they imply no order, because we know the graph really implies 4, 5, and 6 is conditionally independent given the fast, and 11 is marginally independent of 12, 13, and 14. Or the corresponding node sets are independent. So that is important for the final interpretation. Remember, I did say already that we say there is an edge or a node pair is coupled when there is an edge in the graph. An IK path connects two nodes, I and K, by a sequence of distinct edges. It doesn't matter what the edges are. And concurrent nodes are those that are at least connected by one undirected path after all arrows have been removed. And it's not quite correctly posed. Within each set of nodes, each set of concurrent nodes, the nodes are connected by at least one undirected path. So as we saw it before, these are no longer concurrent, even though we started to have them 8, 9, and 10 by the first ordering as possible joint responses. But since there is no path from 9 or 10 to 8, we get different sets, simplifying sets of concurrent responses after analysis. But the joint density is unaffected. First of all, this set of, whenever you have a regression graph, the set of concurrent nodes are unique, and the generated density is not affected when you change the order of the stacked boxes, because there's independence given the past. So now, as I said before, independences are helpful to simplify interpretation, but we're really after dependences in most applications. And therefore we introduce the notion of an edge minimal graph. If you take any one edge away, you introduce an additional independence constraint and therefore a different family. So the formal definition for the edges, when you look at such a graph, we have 3 types of edges, and we need them because the conditioning sets are different in the 3 cases. So if you see a dashed line, you have joint responses, and everything that is in the past of this joint response set is a conditioning set. If you have an arrow, then everything except that explanatory variable that is also a potential explanatory variable in the past is a conditioning set. And when you go to the last, the context variables, you forget about everything that is in the future and model a concentration graph where every missing full line edge means you have independence of I and K given all remaining variables in this context node set, or if the edge is there, it means dependence. So the conditioning set is not changed whether you have defined a dependence or an independences. So nobody yells, nobody screams, nobody asks. No. Okay. Then I go on with more definitions and results. If you want to stop me, you have to ask questions. So we have this split of the node set or the variable set. In U we have the response things, and in V we have the context background variables. And so there are only undirected full line paths in V, and arrows start in V or later and point to nodes in the future. And now we need this nice notion of an interior set of a node. Interior, yeah, this is the whole set. Either it is a direction preserving path. This would be a parent of I. These would all be ancestors of I. And if you take the whole set, connect also to the context variables, we call them interiors of I. And if we take a whole set, a C instead of a single node I, then we get the union of these sets. And we denote them by the interior set of whatever we are just looking at. So now, the two important results regarding regression graphs are based on the definition I have just given you, and the adaptation of the original D-separation theorem that Euler Pearl and his co-workers had formulated and proven to this new type of graph that has three types of edge. So first we need, when do we have an active path, one that induces an edge? Let's think about that first. So if all transmitting nodes are in the marginalizing set, then they introduce a new edge and also a new path. When every collision node is in C or has a descendant in C, then it is in this union of C and its anterior set. And then also an edge is induced that it draws the independence between possible A and B given C. So the global Markov property then has this similar formulation as it exists for directed acyclic graphs or for undirected graphs. We have a partitioning of the node set into two things we are interested in, A and B. Then we have a conditioning set C and remaining variables that we omit or marginalize over. And then whenever there is no active path between any node in A and any node in B given C, then there is independence of A and B given C. So we can read off any independence statement you want, either in the full table or another that you have not in the defining set. And then this last statement was something we had been waiting for a long time. There is really, for these regression graphs, you can obtain read of all independences. So you have a global Markov property if you only know the pairwise dependencies that I have given you in the defining set. That is an extremely important property that holds for directed acyclic graph, but it took a long time until it was formally proven for the regression graph.
Okay. As for the global Markov property, the sets A, B, C are not exclusive.
It excludes M.
Exhaustive for N. They are subsets of the N. Yeah?
Look, N is partitioned by A, B, C, and M.
Yeah.
M is the thing that I'm ignoring. So I could ask, what is the marginal by first ignoring a subset of the variables that are in N or in the generating process, and ask for a marginal distribution of A, B, and C, whether there's independence between two subsets given C in this marginal distribution.
Yeah. Okay.
That is the importance of the global Markov property and why it permits to give you all possible independences you might be interested in. Then there's the other notion of Markov equivalence. I had shown you an example already. And two graphs that are Markov equivalent, first of all, they have the same skeleton, mostly. It can be different, but the skeleton means they have the same number of nodes, the same nodes, the same set of nodes. They are identical regarding their meaning. And then they have the same edge set. It doesn't matter what the edges are. So the skeleton, just remove any specification of an edge. Take the arrows away, take the dashed lines away, turn it into a full line graph. That is a skeleton. You just look at what remains after all the interesting features are gone. So if we have Markov equivalence, then two graphs formulate the same independence structure. And if that is the case, sometimes we have an algorithm for log linear models, but we're really interested in a sequence of directed acyclic regressions. But we don't have an algorithm for that. If the two graphs define the same Markov structure, then we can use whatever we want. And this might pose problems in machine learning because we have no way typically to decide for two Markov equivalent structures by any statistical test whether which one is really the one that we are that is most supported by the data. They are supported in the same way. So the Markov equivalence criterion that we get for the regression graphs is particularly simple because remember this is the collision node type configuration in a directed acyclic graph, and in a regression graph we have the two additional ones that look like this and this and this. And I had shown you last time an example with the data on on childhood remembrance, that one can have these equivalence things. It's a simple criterion. Now, what are the examples of questions that are important, not for statistical research? Much of the research done in graphical Markov models was purely theoretical in the last 30 years. But they're really there to answer questions in substantive research. So, what are the questions that the people with whom I have been working over the years are most interested in? Suppose I have a proper generating process and I get a new set of data which has admitted some of the variables and is possibly for a subpopulation. It's done only for females or only for males, whereas the generating process was defined for the union of the two. So when do the generating dependencies become so distorted that we cannot estimate them from the new study? And then, if we don't want to say directly that our models are causal, we would like to have models that are consistent with causal interpretations. And so we want to understand what is a development over time for other regressions, because one is not clear which is a response and which is an explanatory variable using the same variable set. Or just somebody else has done a subset of the variables and a different study for joint responses, chosen different subsets of joint responses. And then we want to know, is that consistent or not? So it's a more general formulation than what is known as meta-analysis. And then the structure, we want some further question that we have been trying to answer for a long, long time. What happens when we marginalize and condition? Can we construct a graph that still represents the independences and dependences of the generating process for this subset of variables studied under other conditions? And finding general answers to these questions, in small examples you can always do it sort of by hand. It might be tedious, but you can do it. But if you want to find general answers, then you need graph results, and for the graph results, possibly matrix results. And you want to trace graphs, development or paths in graphs, and conclude what happens in a population. And for this, two matrix operators that we have called partial inversion and partial closure, or finding structural zeros, become important. But first I want to make a comment on distortions. We are in the ideal situation when we can do a randomized intervention. English-speaking countries call this the gold standard of a study. So you do by randomly allocating patients to treatments, for instance. And then I had introduced you to over-conditioning and under-conditioning. Suppose we look at the right structure, nothing of that happens. And there are no interactions overlooked with some unobserved variables, a general problem also with randomized studies. Then, we have shown a little while ago, distortions can still occur. And they can be extremely severe. They can change the direction of dependence and the strength of dependence. And they have been overlooked essentially by all statisticians until very recently. And these distortions arise not only by common explanatory variables that have been overlooked, but by marginalizing and conditioning. And the standard example is due to Jamie Robbins and Larry Wasserman. It's now 16 years old. They constructed that particular graph. You see some missing edges, and for instance the past treatment has no edge to the health status because we have such a complete randomized allocation of patients to treatment. Then there is no dependence on anything that is in the past, whether you observe it or not, when it is successful. Then you see a missing edge from TR to TP and to the health status. At that stage, the recent treatment, there was an intermediate outcome after patients have been treated. Then there is a recent treatment. You do not fully allocate a randomized allocation, but you do a randomized allocation depending on whether whatever you did beforehand was successful or painful or horrible for the patient. So you do a conditional randomized allocation. And then we are interested in some outcome for the two past and recent treatment on the patients. And now this is one example of this indirect confounding. You see a path that goes from Y to U to ATP, and that the health status is not fully observed. It's not such a implausible situation. If somebody is delivered to a hospital because it is in a critical situation, you don't have time to do lots of tests, but you try to intervene directly. So now, if you do a regression, suppose the health status is not observed, has been marginalized over, then you still want to know what is the dependence of the final outcome on the recent treatment, the intermediate outcome, and the past. And that means you condition automatically also on the intermediate outcome. But even if you didn't do that, you would regress on the future of the intermediate outcome, and that would make this path between Y and the past treatment active and possibly induce a severe change of the dependence that you see in this set of data without the health status, and when you do a standard regression analysis. And by doing regression, you automatically have explanatory variables, and therefore you can condition. So it is really a very common situation, and it is amazing that it has taken such a long time until somebody has pointed it out.
Yeah, recognize it. So that's the common thing in hospitals, medical doctors.
Yeah. So we said we want to use our graphs. Of course, we need also the estimates and so on. But once we are convinced that the analyses were well done and the graph is a good representation of strong dependencies that we see in the data, the ordering has been given by substantive knowledge beforehand, then we would like to use a graph to say and understand what are the pathways of development, and use the graph to trace dependencies, and not the original long output of statistical analysis. And for this, well, you cannot always do it. You can always do it when you have a Gaussian distribution. But in general, you have to check that certain properties that are common to the Gaussian distribution and to the distributions that are introduced last time, the symmetric binary variables. But there are three possibilities that are not in general true, and therefore one has to check for them. So independences must combine downward or upward, and then the V's that we see have not only to be edge-inducing, but whenever they introduce an edge, there must also be a dependence. So this notion was studied in information theory by Ferro Matos and his student, and then adapted to, in a simpler form, to the graphical models in a recent paper. And the properties we want for the graph then have to hold also in the generated densities. So what does it mean? Independences combine upward, or intersection and independences combine downward. So here it is. I use the simplest possible examples to explain it to you. On the left side, you see a multivariate regression graph. A joint response consisting of the nodes h and k, and one explanatory variable. So if you see an arrow in that graph, it means h is dependent on I, if it's an edge minimal graph, k dependent on I, and there is a dependence between h and k given I. So it takes a while until you can read off these things directly. When I started off using graphs, I always went back to what I knew about parameters in the Gaussian case or parameters in the log linear model to understand whether the graph really represented what I was expecting. So don't expect to know that or do that within a day or so. It takes a little while. So anyway, if we do a backward selection strategy, all of us do that occasionally when we analyze data, and we want to remove the edges hi, ki in the left-hand graph, we are combining two independence statements. And we are left with a graph where we have a single node I that is disconnected from h and k. And for the Gaussian distributions, for linear relations, no higher than main effects, we really then can conclude that the corresponding conditional independences hold as well, given I, so that I is really completely independent from h and k, the remaining edge that is in the graph. And that is called the composition property. And I would say that machine learning strategies or automatic search procedures for multivariate regressions have been using that property all along without telling you about it. And the intersection property, so this we call upward. Upward. Yeah, because you start with two marginal independent statements, and if we have that, it implies given k, given h. And so you introduce an additional conditioning set in the statements, and if we have these two statements, then that follows always. Now look at the other graph here. We also want to remove the edges hi and ki. But here now, the statement is different, that is connected with the arrows. I have a single response I, and then the arrow pointing to I from h. H is a parent of I, given that I have k also as a regressor, as an explanatory variable. So I have hi independent k, h independent I given k when I remove that arrow. Similarly, when I want to, sorry, now I can't do it. I hate it. Yeah, thank you. Good that you sit there. So we remove these two arrows again, and we want to come to the same conclusion. So we start with higher order conditional statements, and we want to conclude what this implies, namely that H is independent of I and K is independent of I. Therefore, I also call it the downward combination of independences. The terms composition and intersection and singleton transitivity that I explain with the next slide have been created in information theory, and when I try to talk to a physician or a psychologist, I wouldn't even attempt to use those terms. They'll kill me immediately and run away or run away. Okay? Is it plausible what I'm trying to say? This, if I have a distribution that mimics these two important properties of a Gaussian distribution, then I really am in a situation where I can use the graphs most successfully. But it needs a third property, and that I call these that are not only edge-inducing, but also dependence-inducing. I told you last time that when I condition on this guy, I introduce this. When I condition on this guy, I introduce an arrow. And when I condition on this guy, I introduce a dashed line. But if I don't have a generating process, but look at something that is induced, then it doesn't necessarily imply that I see a dependence. But when my graph is dependence-inducing, that means I look at a V, I call the inner node O and the outer nodes, for instance, what, I and K, huh? I, O, and K. So in that case, it is edge-inducing when I marginalize over it, and if I have an edge-minimal graph, that really means I is dependent on O and K is dependent on O. So what this statement, this dependence-inducing property then means is it cannot hold that you have conditional independence given the source and marginal independence. But whenever you ignore the inner node of a V, you introduce a dependence. And so whenever I have a collision node, that is in something in the future, so to speak, from the outer nodes. And therefore, it's not included in the conditioning set. No matter where the inner node is not included in the conditioning set, no matter where you are in the graph. So the graph implies I is independent of K given some set C. And then if you condition on this inner node, you introduce a dependence given C and the inner node. And if you have this type, one of the many transmitting V's, then this means always, no matter what the other C is, conditional independence given some set C and the inner node. And when you now ignore the inner node, you marginalize over it, you introduce a dependence when you ignore O. And so these are the three properties. Independences have to combine downward, upward, and dependence-inducing V's have to introduce not only an edge, but a dependence that is associated with that thing. So
could you show a graph for the second statement?
this is the graph.
Are you okay from the transmitting V?
Here's a transmitting V, and I have lots of other things that go in here. And this is C.
I see. Okay, that's C.
So this is conditionally independent of C and O. That's what the graph implies. No matter what the C is, if C is a subset of the node set, excluding these three. Okay. And so now, if you ignore that, you introduce a dashed line here, and then we want to interpret that this is a real dependence.
Yeah, they have dependence.
Okay? So, okay, now I turn to partial inversion. Partial inversion was derived, well, I've been a student of Arthur Dempster who studied the sweep operator by Beaton intensively. So I was familiar with that particular type of a matrix operator, and it didn't quite do what we wanted. So this sweep operator or Cholesky factorization only works on positive definite symmetric, so on symmetric matrices. And here we want to have matrices that are just square. Every principal submatrix, that is one that includes the elements on the diagonal, is indeed invertible. And then we order the things so that they can be written easily in matrix form. So you have a corresponding vector y and x, and you multiply the x vector in terms of m. So you have a set of linear equations if you want to. And the linear relation after partial inversion, this is the partial inversion operator, and I tell you later on in the next slide actually what it is actually doing. But from the conceptual understanding, it exchanges the picture and the explaining feature for just the subset. Okay? And here's the simplest way of describing this operator computationally. So if I want to operate just on a single row and column, I say I want to invert my matrix just on index I1. And then there is a scalar in my matrix in position 1, 1, and a vector, a row vector, and a column vector, W, in the other positions, and a matrix, small m, in the rest. So after partial inversion, you have transformed the original matrix M in the way you see there. You introduce the pivot element, you change it into the reciprocal, you divide everything that is in the row by S and change the sign. You do the same in the column. And then the final change is a vector version of what is known for a long time as the Schuh complement, I would say. Yeah, the Schuh complement. So, and the beautiful trick here is that if you want to understand what you could do it, you don't really have to, when you have a computer, you don't really have to change things. But if you want to write it in terms of matrices, you just permute the thing. If you have first, or you do the partial inversion in 1 and then on 3, then you have an outcome of the first operation, put the 3 again in position 1, 1, and repeat the same simple operator. And this whole thing has a history that goes back almost 3,000 years, because it was studied already in a Chinese book on solving linear equation at that time. Later on it was called Gaussian elimination, because Gauss was named after everything, more or less. And there is a beautiful paper in the notices of the American Mathematical Society in 2011 that shows you endless historical and different types of development. The Gauss-Doolittle method, the Cholesky factorization, the Gauss-Schmidt orthogonalization. Lots of things are named after it and have been done. Gram-Schmidt. Yeah. And I think this is now really the I remember that I opened Snedeker and Cochrane and had to learn about the Gauss-Doolittle method in it, because Cochrane asked us to invert a 5x5 matrix by hand. So, I hated it. And now we have this simple operator that can do it. Just apply the same type of thing again and again.
Take a break.
Yeah, we can take a break. But let me go through this example of partial inversion that is possibly familiar to some of it, and it helps me to introduce some notation. Think of a covariance matrix and that it is positive definite, so that you can invert it. I write the covariance matrix when I partition it in this form with subscripts and the inverse with superscripts. And from the properties of partial inversion, we know that inverting the covariance matrix on A must give precisely the same answer as inverting the concentration on A must give the same answer as partially inverting the covariance on the complementary subset. And indeed, if we write the outcome of then we can write it in nice closed form, and that indeed the concentration matrix can be used to define a conditional the parameters in a conditional distribution and in a marginal concentration matrix has been observed by Dempster. How long ago? 40 years ago. Okay. So I will have a break now.
Okay.
5 minutes?
5 minutes, yeah.